sounds good. Yeah, sure. Don't worry. Yeah. I just told a little bit about the background. Like nowadays, when people want to learn a function, people usually learn it in an end-to-end manner, where you carry out the function, compute the loss, and do like gradient descent for optimization. So this is very, very popular in like say recognition tasks. So you can see on the left side, like this is the usual way when people do classification, for example. However, if we look back in history, this is not always the case in history, even for recognition. So before ImageNet become popular, the layer-wise training was a more popular solution. So when people are before ImageNet, people are doing layer-wise training, where every layer is trained separately while keeping other layers frozen. So the network is growing like layer by layer, and they are only combined at inference time. So this is kind of the history of recognition, where people shift from layer-wise training to end-to-end training for recognition models. Yeah. And nowadays, like generative modeling have been very, very popular, but the most popular paradigms like diffusion or flow matching and autoregressive models, they are similar to layer-wise training because they each decompose the generation process into many, many steps. Like diffusion will decompose it into like say a sequence of denoising steps, while autoregressive will decompose it into a sequence of like say token by token steps. And then the steps are trained separately and only composed at inference time. So this is kind of the current status of like the most popular generative modeling approaches. Yeah. And if because of this nature, if you zoom in the diffusion process, so this is a quick recap. I think like most people already know a lot about diffusion, but the diffusion process basically decomposes the forward process, like gradually transforming an image into noise into a sequential steps of adding noise. And then the model learns the reverse process, which is also a sequential process of gradually removing noise. As a result, at inference time, the denoising steps are carried out iteratively, and the distribution evolves iteratively at inference time from a Gaussian noise distribution to a slightly less noisy distribution until like finally to the data distribution. So this is a recap of diffusion, where the distribution evolves at inference time. And here is a like say visualization from Twitter. Like throughout the inference, you can see like the distribution transforms from one distribution to the other at inference time. Okay, so this is a recap of flow matching and diffusion. Yeah. And here, yeah, those are about background. And the core idea of this work is like instead of evolving the distribution at inference time, you want to design a training paradigm, like a training loss, to evolve the generative distribution throughout training. Okay, so this is a high-level idea of the drifting model, which we are proposing now. Yeah, so here is a visualization. Ideally, we want like throughout training iterations, the generative distribution gradually evolve to the data distribution. And there's some laws in order to make this happen. Okay. And this is another visualization where you can show like throughout training, the distribution converges to the data distribution. Okay, so this is the idea we want to propose, like the most high-level idea. And in order to do this, now we want to define a training loss which guides the generative distribution to evolve to data distribution. So here's the core concept. So we define a drifting field, which is a vector field depending on the current data and generative distribution. And given area x in the d-dimensional space, it will give it a vector, a drifting field vector, telling it where to go. So with the drifting field vector, we can define how the distribution evolves. That is like let Qi be the current generated distribution and P be the data distribution. For every sample in the generated distribution Qi, we want it to move according to the drifting field V. That is like after one training iteration, we want Xi to move to the location of Xi plus 1, which equals like say Xi plus the drifting field V. Yeah. And finally, we want the evolution to have the correct equilibrium. That is, we want the condition that when P equals Q, the drifting field V equals 0. under such condition, we can ensure like when P equals Q, the system will stop moving and it will be an equilibrium point. Okay, so this is a high level like conceptual framework in order to drive the distribution evolution. Any questions so far? Okay, if not, we can move on. Yeah, so now we have this most high level framework, and we want to turn this framework into some like say loss function in order to drive the training. So our goal of such training is to make the xi shift towards like xi plus v after one training step. Yeah, so if we parameterize xi by a neural network, and we let zeta I be the like say parameters at the ith iteration, what we want from the training is that we want after one training step, the like say the same epsilon is mapped to the position which is the old position plus the drifting field. Yeah, here we parameterize the generated distribution qi by the output of the neural network f zeta I, given like say some input from some prior distribution, which is epsilon. Yeah, and we want like say the output to shift to the old output plus the drifting field v. Okay, and in order to encourage that, it can be transformed into a very straightforward loss function, which is we encourage the output of the neural network given epsilon to the old output plus the drifting field v. And conceptually, like this part is from the old neural network. So we apply stop gradient to it because conceptually it comes from like say the old copy of zeta. So in this way, we can obtain a loss function to encourage the distribution to evolve based on the drifting field v. Yeah, and these are the high-level framework. And the exact instantiation in the paper was the following design trace of the drifting field v. Although I know like lots of other design traces might also work. Yeah, but this is just one instantiation in the paper. So in order to design such a v, what we want is like when p equals q, such a v should be 0. Yeah, and in order for this to happen, like the instantiation in the paper is based on mean shift, which is for every particle x, we compute the local centroid of the generative sample, which are the blue dots in this figure, and define the local centroid of the real sample as like say Vp plus, and we also compute the local centroid of the generative samples, which are the orange points. So in this case, the local centroid will be Vq minus, and we define the drifting field to be shifting towards the difference of the local centroid. Yeah, so these are the like say precise definitions. So basically for every other like say y plus, which is a data point, it's weighted by how close it is to x, and for every y minus, it's also weighted by the same like say how close it is to x. Yeah, so this is the instantiation of the drifting field in the paper, and this drifting field can be estimated using mini batch. So you can sample some like mini batch of like say y plus and y minus, and you can get a Monte Carlo estimation of this drifting field. Yeah, so this is the instantiation in the paper. And with this instantiation, if you train a neural network, you will see like the generated distribution converge to the data distribution. And there are several signals here. First, you can see like through iteration, the distribution converges as expected. And the second signal is that there's no mode collapse problem. So if you look at the third figure, actually initially the generated distribution all start from one mode, but throughout training it will also discover the other mode and cover the entire data distribution. Yeah. So any questions so far about the instantiation of the framework? Okay. If not, let's proceed. Okay, so this is a drifting field framework and the instantiation in the paper. And this framework can be extended to many, like say, different extensions. For example, one thing is like the loss can be defined on a feature space. So when two distributions P and Q match each other, a natural like say implication is like the distribution of their features will also match each other. So as a result, you can also define the loss on the feature space, where like phi is a feature extractor and you define the laws to be like let the features drift based on the drifting field computed on the feature space. And you can also combine the laws of multiple features together. And even if you combine lots of them together, a good property is like P equals Q will be a common minimizer for all of them. Because when P equals Q, the distribution of phi will also match for the generated and data distribution. So the laws on the feature space will also have an equilibrium when P equals Q. So P equals Q will be a common minimizer for all of the feature space losses. So you can combine them very freely. Yeah. And another extension is CFG, where like say CFG is a very popular solution in generative modeling, where you want to like say sample high quality images by extrapolating the generated distribution from the unconditional distribution. So you want to generate from the extrapolation of conditional from unconditional distribution. And in this like drifting framework, you can also do it by mixing some unconditional samples into Q. Yeah, so in this way, the Q will be a mixture of generated sample and unconditional sample. And when P equals Q, the generated sample will be an extrapolation of conditional from the unconditional samples. Yeah, so this is just one natural extension. Yeah. And we also want to discuss a little bit about the relationship to like related works and prior like say methods. So if we compare drifting models to flow matching or diffusion, the conceptual difference is that we want to evolve the distribution at training time, while like say multi-step methods like flow matching or diffusion try to evolve the distribution at inference time. Yeah. And we can also compare like the drifting field to earlier one-step models. And one finding was that earlier one-step models usually have an underlying drifting field. So for example, if you're optimizing some loss function L, with respect, like say you're optimizing the distribution Q to minimize the loss function L, with some math, you can derive like the samples are moving according to the drifting field V, which is the nabla of X of like say dl over dq. So under such, but however, it's not vice versa. So if you have some drifting field, which is like say satisfies the correct equilibrium condition, it doesn't require it to be integratable or to have an underlying L. So it's like the drifting field is a superset of the like say optimizing some loss function L for your generated distribution. So this relationship is similar to like energy-based model to score matching, where like say in energy-based model, like the centric is the energy function, and for every energy function there will exist an underlying like score function, which is its derivative. But when people are modeling the score function directly, they usually don't require the score function to be integratable, or the centric is the score itself. Yeah, and the score itself has like say many like say properties. Like it can be estimated by a neural network. It doesn't need to be integratable, and this flexibility is helpful. And in this case, like if people are optimizing some loss function L, there will always exist an underlying drifting field. But when you are like say using the drifting field to get your training, there doesn't need to have an underlying L. For example, for the instance in this paper, I don't know if there exists an L or not. Yeah, and also like by focus on the V, you can do lots of like say normalizations or stuff some V directly, which is also very helpful. So this is a relationship like to the methods of optimizing a loss function from a high level. And some concrete examples was like if you look at like say MMD or Coulomb GAN, there exists some underlying V. If you look at like say DMD, which is distribution matching distillation, there also exists some underlying V. And when like say you look at GAN, there's also some underlying V, which is just the derivative, the gradient of samples with respect to the discriminator. Yeah, so this is a conceptual like say relationship. Although in different works they have different instantiations in order to estimate this V, whether it's using like say Monte Carlo plus feature space in this paper, or like say for lots of prior methods, they require like say alternative or adversarial training of two neural networks in order to have a correct estimation of this V. Okay, so this is the relationship with related works. And now I'll move on to describe the experiment results. So the first conceptual experiment is on TOI. On the TOI data, there are two signals. The first signal is like the model converges to the data distribution throughout training. And also the loss is stable and it's basically decreasing throughout training. And another experiment was on the ImageNet. So for ImageNet training, we use the following setup. So first, we define the loss on the feature space using a pre-trained encoder. So loss function is defined on, like, say, activations of a pre-trained encoder. And we use class conditional generation. We are, like, say, given a class label, we generate, like, say, samples. And in order to train the class conditioned model, we do the following training. So for every training step, we sample some like NC number of class labels. For every class label, we generate N many images, and we sample N pulse many real images from the data set. And we estimate the drifting field V within every class. Yeah, so this is the setup. And when we are talking about epochs, it's measured by the total amount of generator forward passes, which is NC times N pulse. So in this way, the generator flops is comparable or the same to flow matching. Okay, so here are the experiment results. So the first important signal is that the correct equilibrium is very important. So if you change the drifting field to something where, like, say, the attraction outperforms repulsion, or when repulsion outperforms attraction, in both cases, you'll have very bad samples. So, like, say, if you look at the samples, you'll see like they are out of distribution of the data distribution. And the reason for that is like the equilibrium is changed when the drifting field V doesn't vanish when P equals 0. As a result, the equilibrium will be some weird point where, like, say, the generated distribution will fall off of the data manifold, and you'll get bad generation results. And the second signal is that if you have a better estimation of the drifting field V, you'll have better results. So here in this paper, we are estimating the drifting field V using some, like, say, Monte Carlo estimation with some amount of data samples and some amount of generated samples. And if you only have one positive sample, it works. However, the training is much slower. And we found, like, say, if you increase the number of positive samples, or you increase the number of positive and negative samples per class label, in both cases, we keep the, like, say, the total number of forward passes of the generator the same. But in both cases, we found, like, say, there's a monotonic increase in FID if you have a better estimation of the drifting field. Yeah, so a better estimation actually helps. And another interesting signal was that regarding to the feature space where the drifting loss is applied on, we also observed a scaling law where, like, when the drifting space is become like wider and wider, or it's trained for longer, or it's trained plus some like classification fine tune, we see like monotonic increase in performance. So here the setup is that we train our own, like, say, MAE model on the latent space, and we use different sizes of the MAE model and different amount of, like, say, training epochs, and we see a monotonic gain. Although the method also works with, like, say, pre-trained feature models like SimClear or Moco, yeah. But in our case, by default we use the latent MAE because it avoids backpropagating through the decoder, and it allows us to conduct, like, say, scaling experiments like here to see the scaling behavior of the feature space. Yeah. And finally, for all the ablations, it was conducted with only 100 training epochs of the generator. And when we scaled up the training epochs, we actually observed state-of-the-art performance on both latent generation and pixel generation. Yeah, so, like, say, when we train the model for longer, it actually outperforms prior methods on one-step generation. Yeah, and here on, like, say, uncurated samples for class conditional generation without, like, say, CFG guidance, and they generate like reasonable samples. And yeah, and in another experiment in the paper, we validated the samples are not memorization from the training set, but they're actually like say generalizes to some novel samples. Okay. And we also have experiment on robotics, which like follows the diffusion policy, like say set up. Given some observation chunk, we try to predict the next chunk of actions. Yeah, and in robotics, we only apply the laws in the raw space without, like say, use features, and we only have one positive sample. And the result was like we observed competitive results to diffusion, like say policy with 100 forward passes using only one, like say, forward pass of the neural network. Yeah, so this is also very promising on the robotics side. Yeah, so a takeaway or summary for the finding was that in this paper we proposed drifting model, which is a framework for guiding the distribution to evolve at training time. And the conceptual idea is just like we define some drifting field V, and we just move samples according to this drifting field V. So, and we turn this into a loss function by regression, the samples to the target sample, which is the samples moved with V. Yeah. And one instantiation we showed in the paper was that we can actually estimate V using mini batches, and we can use feature space to handle the curse of dimensionality, and the method actually scales with the feature space. Yeah, so these are the findings of the paper. Yeah, and that's it for the talk, and I'm happy to discuss or answer any questions.
Thank you so much, MingYang, for amazing talk.
Yeah.
So I'll start with a question, and if anyone has any question, they can unmute and ask. So you talked about using feature encoders for larger experiments. So did you use pre-trained encoders, or do you think using pre-trained encoders can have better effect, or do you train these from scratch?
Yeah. So we have both experiments in the paper. So like the SimClear and Moco V2, they are pre-trained feature encoders. Like they pre-trained, like they self-supervised feature encoders. And for these, like say, for this experiment, we trained it on ourselves. So they're just like say MAE trained on the latent space. They're frozen through our generator training. So in this sense, like they are pre-trained because they never changed in the like generator training, but we train them from scratch. So we train our own like say latent MAE models, like say a MAE defined in the latent space.
Yeah, sounds good.
Yeah. And thank you for the question. Yeah.
Yeah, this sounds great. Like I was looking at the initial like the drifting features and the diagram that you had. This kind of looked like the energy-based models. Like you have very much thought about from your the first principles, and I just wanted to ask about the drifting. So, is that directly the from the framework that you calculate? Do you kind of in the feature space, do you dynamically try to change based on your encoder space, or like maybe there I don't know if you have tried or experimented with that here, but maybe a future direction that I like, if I have time, I may experiment with is with respect to like in the latent space, how do those features kind of drift, and which you have here looked at, but from a dynamic perspective, in which those features have a hierarchical representation, and you are trying to change it based on like the objects that you are like trying to work on.
Oh,
So,
yeah,
like,
sorry.
yeah, have you thought about that, or like, do you have any such sort of like ideas in your mind?
Yeah. Sorry, would you say the question again? I don't fully get it. Are you asking about the training dynamics or training evolution of the feature space or something? Yeah. Sorry, I don't
Like,
fully get the question.
yeah, like this is like this is not related to this. Like I'm just speculating or thinking about how kind of a adaptive hierarchical based feature space can work, specifically when you are trying to look at multiple objects or a complete scene. So this is like in the space of pure ideation right now. So this just came into my mind, like based on the research that you uh, presented. It might work or it might not, but like, yeah, feel free to comment or ignore my
Yeah.
query.
Yeah. So sorry. Yeah. I will try to understand. I will try to answer based on my understanding. Yeah. Thank you for the
Yeah.
question. I'm not sure if I fully get it, but if you are
Mhm.
talking about like say, yeah. So one finding, yeah, I can share was that in this paper, the feature space was hierarchical. So there was like say a pyramid of features where like say because the feature encoder, the architecture is a ResNet, so there are
Mhm.
different resolutions of features. Although the generation is one step, but the loss function is applied on the feature pyramid. And I
Mhm.
found it to be like very helpful. Yeah. And for the generation, yeah, I feel like the generation, like if you want to cascade it or do something, you can also make the generation hierarchical. Yeah, but I
Mhm.
feel it will also work because one step generation is usually harder. Yeah. Yeah,
Yeah,
but
yeah.
I'm not sure if it answered the question. Yeah, but that's just
Yeah,
like
yeah,
my
yeah. Like
understanding.
in those dynamics, this idea can work or may not, but like I was just trying to combine those thoughts. Yeah, thanks.
Yeah, thank you. Yeah.
One more short question that I had in my mind was regarding the training cost compared to diffusion model.
Yeah.
So, do you think it is more costly to train as compared to diffusion models?
Yeah. So I think the training cost is comparable because here when I talk about 100 epochs, it's 100 epoch of generator for the passes. So this part basically has the same cost as training a flow matching or diffusion model for 100 epochs. Yeah. So this part of the training cost is comparable. The only additional cost is that you have to like say send your generated samples through the feature encoder. So that is an additional overhead. But that's just like say like 50% of the time. So in this case, I feel the training cost is comparable to diffusion or flow matching models.
Right. Sounds
Yeah. Yeah, thank you for the question. Yeah, I feel it's a very good question. Yeah. Yeah. Any more questions? If there's no, we can also like say call it a day or
Yeah. Thank you so much,
yeah,
Ming, for
sure.
amazing
Yeah,
talk.
yeah,
It was a pleasure having you.
yeah. Thank you so much. Yeah, also very honored to be here. Yeah, thank you for the invitation and have a good day. Bye bye.